This conversation is powered by Google Illuminate. Check out illuminate.google.com for more.
Ever wondered how lasers work? It's not just magic, you know.
Nope, definitely not magic. It's physics, and some pretty cool physics at that.
And today we're diving into the nitty-gritty of laser pumping, a fascinating simulation.
It's a great way to visualize a complex process, yeah.
So what exactly is laser pumping and why is it so important? So break it down for me. What's the basic idea behind laser pumping?
Essentially, it's about getting the atoms in a laser medium excited to a higher energy level. Think of it like charging a battery.
So you're giving them a boost of energy?
Exactly. That energy boost is what we call pumping. Without it, no laser, right?
And how do you actually do the pumping? Is there just one way?
Nope. Several methods. Optical pumping using light is common. Electrical pumping using electricity is another.
So like shining a really bright light on it or running a current through it?
Precisely. The simulation shows optical pumping, which is visually easier to understand. This simulation, it's pretty neat. It shows the population of atoms at different energy levels.
Yeah, it's a great visual representation. You can see how the pumping rate affects the population of excited atoms.
And then once you have enough excited atoms, you get lasering.
Exactly. The simulation shows the lasering rate, which depends on the pumping rate and other factors.
The simulation shows energy levels E1 and E2. What's the significance of those?
They represent specific energy levels within the atoms. The transition between them is crucial for laser emission.
So the atoms jump between those levels, releasing energy as light?
Precisely. The pumping rate determines how many atoms are excited to E2, and the lasering rate shows how many make that transition back to E1, emitting laser light.
The simulation also shows percentages. What do those represent?
Those percentages represent the proportion of atoms in each energy level. You want a high percentage in the excited state, E2, for efficient lasering.
So a higher percentage at E2 means more potential for laser light?
Exactly. It's all about maximizing the population inversion.
The simulation credits Fuquan Wang and Lukang Wei. And it's open source, right?
Yes. It's released under a Creative Commons license, meaning it's freely available for educational use.
That's fantastic. Making science accessible is key. The simulation is hosted on iwanttostudy.org. Is that a good resource for other simulations?
It seems to be a hub for educational resources, including many physics simulations. Worth checking out, yeah.
What other aspects of laser physics could someone explore after understanding pumping?
They could delve into different types of lasers, laser applications, or the underlying quantum mechanics. It's a vast field, a really vast field.
And what are some real-world applications of lasers that rely on this pumping process?
Lasers are everywhere. From barcode scanners to laser surgery, the applications are incredibly diverse.
So laser pumping is the key to getting those atoms excited enough to produce laser light.
Exactly. It's the fundamental process that makes lasers work.
And this simulation is a great way to visualize it. A really helpful visualization. That was a great discussion. Thanks for breaking down laser pumping for us.
My pleasure. It was fun.